Hello everybody and welcome to my Golang course. In this course I will explain many of Golang topics from the beginning with more details. Okay, so let's go. Golang installations is very easy, so I will not explain it. I am using Golang IDE. It's from JetBrains. I love this one and all JetBrains IDEs. So you can use this one or IntelliJ or Visual Studio Code. It's free or anything you like. Let's go. Welcome to Go. Okay. If we run it, will not run because it doesn't have the package main. So we need to change this to main. Okay, now it's running. Okay, welcome to Go. So package, it's a logical way to organize the program and also can be physical, like directories on the hard disk. So package can have one or more source files from Go source files with the extension Go, and they organize the program as we said. So you can have package for math, package for web, for package for database, and these things. Okay. The function main it's the entry point for any Golang program. Without it, we cannot run the program. Okay. If we say this, what's this? It is not a program. Okay. We import package, another package here. Okay. Goland shows us where is it, and in fact it is on our Go directory where we installed Go. Okay, we can find it under src and anyone fmt for example, then print source file. Okay, so this is the package. It has these all files. They are all belongs to fmt format package. Okay, what we have or where do we use it? Did we use it here? Okay, println. So println function, it's inside print.go file, which it belongs to fmt package. Okay, we will take functions later, so don't mind now. Okay, so fmt, this is the package. Then we call the function and we send this string to this function to print it. So this is a very basic Golang program. Okay. We can say dot and then delete this. Okay, and it's okay. Maybe it appears good, but I don't prefer it. I prefer calling with packages. It's more clear and can be understood faster. Okay. So after this we will talk about data types, because data is the most important thing we have in computer. Data and processing this data. It's all what we have, in fact, nothing else. Everything is about data, or could be just data, and of course about it, but the core is data. So what data do we have in Go? Let's keep this all the time. Okay, for now. We have multiple data types. Okay, we know that. Okay, let me do something. File to explain. Okay. File data. Computers at the end or at the beginning, how you want to say, just use zeros and ones. Okay, zeros and ones as you go. Okay, another words we can say numbers. Okay, everything is a number. In fact, everything is zeros, one, and this one is combining them makes a numbers. So we can say everything is numbers. Numbers are numbers. Okay, integers, float, characters are numbers, strings are numbers, images are numbers. In fact, each image has number of pixels, and the pixel is just a number. The colors are numbers. Okay, the computer, we cannot deal with other thing. Okay, we can build on numbers by numbers. In fact, to see something that we can uh, say it's not a number. Okay, it's an image. I see the image, but the computer doesn't see an image. It sees the numbers. Okay, so numbers. So what data type is for numbers goes have. Okay, go has first integers. Okay, let's say one integers, two floats. Okay, three runes. Fine. We have complex numbers. We will not talk about them. They are very simple and they are floats. Okay, but this nature of complex numbers. For math, for engineering, they use it a lot. Okay, sometimes you need to use them. Okay, let's talk about integers. There's a lot of speech we can say. So integers. Okay, integers. Integers are natural numbers that doesn't have decimal point. Okay, like 1, 10, -5 or -6. Uh, Bigger the point or small. Okay, the smallest one is in minus. Okay, I don't know, minus 1 trillion or more. It's according to the size of the integers, and we will see this. Okay, so this is integers without decimal point. Okay, but there is not one integer type in Go. In fact, we have 10 integers. Yes. So let's say integers. 1, it's integer. 2, it's integer. 8, integer. 16, integer. 32, and 5, integer. 64. Okay, we will see the other 5, but now let's talk about binary. Okay, integer 8, 16, and 32, and 64. This is the size in bits of the integer. Okay, so integer 8, it contains 8 bits and just 8 bits. So the value can be stored in 8 bits. Okay, let's see. For example, let's say 0, 0, 0, 0, 0, 0, 0, 0. This is 8 bits. Okay, they are zeros, but for example, for 5, this will be this. Okay, 1, 0, 1 from right, and the others are 0. This is 5 in our system, decimal. Okay, we use decimal system for numbers. Decimal system contains 10 digits. Okay, from 0 to 9. These are 10 digits, so it's with base 10. Okay, and after 9 we reuse digits from the beginning. So after 9 it becomes 1, and then 0. Okay, so this 9, when we add 1 to it, we do 1 here and 0, of course, and then tick. So this will still until we goes to 9. So this will be 2, this will be 0, and so on. Okay, so this is our system. But computer is binary. It it understands this. Okay, so 5 in our system, in decimal system, is 101 in binary system. Okay, why it's 101? Okay, binary system is consists of two. Okay, two digits, 0 and 1. This is the states. Okay, or the combination, or combination can be done from this, 0 or 1, nothing else, not 0 1 2 3 4 like us. So from right, the first digit, it is 0 to the power, it's 2 to the power 0. Okay, the second is 2 to the power 1. The third is 2 to the power, not here, 2 to the power 2. Okay, and then 2 to the power 3, and so on. Okay, so now 2 to the power, it's 8 plus 4 plus 2 plus 1. Okay, it's multiplication of 2. 1, 2, 4, 8, 16, 32, 64, 128, 500, 256, and 500. 12. Okay, so after this, 1024, and so on. Okay, so it is multiplication of 2. Now this, if they are existed, it could be existed or not. Okay, so to figure out, or to make 5 from this should be 0, because 5 is less than 8. Okay, 4 should be 1, and this 2 should be 0, and just this one should be 1 also. So because 1 plus 4, it's 5. Okay, so 101 here. Okay, this is from where it comes, why 5 is 101, or why 101 is 5. I hope this clear. So when we say that it is integer 8, this means that it consists of 8 bits. Okay, but these integers are signed. Signed means they can hold negative and positive numbers. Okay, so how on the low level of bits we can distinguish this? Is it positive or is it negative? They use the first bit from left for this. If it's 0, then the number is positive. If it's minus 1, 1. If it's 1, this one, then the number is negative. So let's see this by our eyes. Print. Okay, print f. It's another function to print in Go, but it uses format, so you can control the output very well. Okay, it's not dedicated in Go or to Go language. It's from C. There is printf, C, C++, Java, PHP. This, I'm sure they have it. Also, I think JavaScript. It takes everything from other languages. Okay, so let's say V and here B. This called format verbs. Okay, not because this this V is for value, but this percentage with the letter, it's format for printf. Printf, it's a print format. Okay, so if we say 5 and then 5 here, okay, it will print 5 and 101. Fine. If I want all zeros, I will say this 8 to take 8 not spaces, in fact. Okay, space. It's not a space like nothing, but a space for with it. Okay, with it to print, and this to become zeros. Okay, before the number. If there is nothing, zeros. If I say whatever, for example, if I say this will be this. Okay, but now we are okay. It has meaning. So okay, all of it has meaning. One. Okay, it can't be with binary, I think, yeah. But we need zeros. Okay. So zeros until we have this. This is better. This is 3 digits. 4, 5, 6, 7, 8. Fine. Okay. If it's negative now, we see for this digit, it will become 1. Okay, it doesn't say 1, it says negative. But it, of course, it disappeared. Okay, we have just 7 bits here. But this, it's 1 in fact. Okay, so let me write it like binary. We can write numbers immediately as binary. Okay, 1, 0, 0, 0, 0, 1, 0, 1. Okay, parenthesis added. Okay, but okay, not let's see decimal. Okay, does it takes it as unsigned or what? Cannot convert expression of type integer to integer 8. Okay, but I don't want it to be integer. Okay, by default is integer, so we cannot do this. Okay, to your integer. 8. Yeah, integer is okay, but it still this. Okay. Okay, because it doesn't see it like a negative. It is like positive, and this 132 cannot be contained in integer 8. Okay, you integer 8 can unsigned. Okay, we'll see this. But this is the point. This for signed numbers, the first bit is for sign. Okay, so still this. Okay, fine. So this is about binary. There are two other systems. There are hexadecimal and there are octal. Okay, it will not change for hexadecimal and octal, but okay, let's say x and is it okay, this is binary. This will be the same. Let us make it 10. Okay, fine. This is in binary, 1010. This is A in hexadecimal. Hexadecimal goes from 0 to F. Okay, and this is for octal. Octal goes from 0 to 8. Okay. Octal from 0 to 8. So after 8, what do we have? We have 1010. Okay, and then 11, and then 12. In decimal, after 8, we have in fact it's octal. It doesn't to 8, it's to 7. Okay, it 8 digits from 0 to 7. So after 7 we have okay, 10, 11, 12. Okay, and we after 8 after 7. Okay, we have 8 and okay and this. So 10 in decimal is 12 in octal. Okay, for hexadecimal okay, we have 10 and okay, not 10, we have Okay, 9. After 9, it goes A, B, C, D, E, F, G. From 0 to F, not G. Okay, so 9 here, it's our 9, no problem. But our 10, it's A, okay. After F, it goes to 10, but 10 in hexadecimal is 16 in our system, okay? If we say 16, 16, and 16. Okay, it's 10 in hexadecimal and 20 in octal. Okay, it's not detailed, but I think it's enough to understand the things about systems and all of this for our integers. Okay, so integer 8, 8 bits, integer 16, 16 bits, 32, and so. Okay, so okay, why this difference? Why there is integer 8, 16? It's for memory. Okay, integer 8 bits, just 8 bits, and of course we cannot store all numbers that we can store in integer 16 in integer 8, because integer 8 can hold less numbers or less range of numbers. That's clear. It's just 8 bits, like you have 8 boxes. You cannot take all things from 16 boxes and put it in 8 boxes. Okay, you need another 8 boxes, of course. Okay, you cannot compress bits. Okay, and this level you can compress numbers or characters, but at high level, not on the bits level. Okay, so how can we know the maximum values? Okay, the maximum value, let's say, and the minimum value for each one of these. Okay. This can be, it's 8 bits. Okay, before this, let's say that in our system, in the decimal system, okay, we have 3 digits. Fine, 3 digits. Or okay, so in these 3 digits, what's the maximum value we can store? Okay, 3 digits like this. We know that the maximum value is 999. Okay, why this? Okay, we know this. This is our system. We deal with it every day, so we know this. Okay, but of course, from mathematical perspective, we can have a proof uh, or origin of this, from where it come. Okay, so we have 10 digits. Okay, 10 the primitive numbers of our system. Okay, and we make power it to 3. Why? Because we have 3 digits, and of course this gives us 1000. Okay, but the 0, it included in the positive side of these numbers. Okay, it is 0, it's included, so we must subtract 1 and we get this. Okay, so this is how we know that 3 digits in decimal system, it's not the maximum number, it's 999. Okay, so for our integer 8, we don't have 10 digits, we have 0, 1, 2 digits to the power 8, then minus 1. Okay, from the beginning. Okay, but this is not to the power 8. Why? It's into 8 bits, but we said that the high bit, or the bit of the first bit from left, it is dedicated to sign. So we have, for the value, we have just 7 bits. Okay, so 2 to the power 7, it's 128, minus 1 becomes 127. So this is the largest number we can store in integer 8. This is in the positive size. In negative size, it is without. Okay, it is 2 to the power 7. Without what? Without minus 1, because 0 is included in the positive side. So here it is 128 minus, of course. Okay, I hope this is clear. The same for 16 bits, for 32, for 64. Okay. Okay, so let's see this here. Okay. empty print. Okay, print what? We have max size, not max size, integer 8, max. This is the package. This is a constant. Okay, we'll see how it works. So it will give us 127. Okay, the same of our calculation, but it didn't do it with multiplication. It did it with shift lifting, and I will explain this very soon. Okay, let it open. Fine. For 16, it is 67, 32. 67 is for unsigned. 32, 767, okay, and so on. So this is the largest, okay. If you want the size of, okay, we have unsafe package, have function size of integer 8. Okay, it cannot take integer 8, of course not an expression. Let's say anything. Okay, convert 0 to integer 8. Okay, this doesn't have line. Okay, it's 1. Okay, 1, it means 1 byte. We know that 8 bits makes 1 byte. Okay, 2 bytes means 16 bits. Okay, so the size of integer 8, it's 1 byte. Okay, if you wanted to in integers, in bits, we multiply by 8. Okay, so we can say 16, 16, and so on. Okay, we can say 5. This will give us 64. Because integer, this one, okay, I didn't mention it. Integer without size, bit size, like this, 4, it is machine dependable. Okay, machine dependable means that its size depends on the machine. If the machine is 32 bits, it will be 32 bits. If it's 64, it's 64. So my machine is 64, so this shows 64, okay. I can say integer, but it doesn't require this because it's by default, any integer number by default is from this type, and it's integer, and it's 64. Depends on the machine. These types are not machine dependable, they are machine independable. So they are with the same width on any other machine. Okay, here it's 8 bits, there it's 8 bits. So no difference. So they are portable types. We can say portable types because we will not expect any other behavior of them. And imagine that you work on 64 bits machine, and most of today machines are 64, but for some reason the program has been run on what, on 32 bits machine. Okay, this can make some problems. Okay, because in your program on your machine you store a big value that can be held in 64 bits integer, but in the 32 it cannot be. So sometimes or many times it's better to declare or use this one, that machine independable. Okay, integer is fine now. Okay, that's good. The others 5. Okay, let's say 6. They unsigned. Okay, you integer 8. Okay, what do you know? Take this, put this. Oh, okay. I will take them from the beginning. Thanks to, I don't want to arrange. Okay, 7, 8, 9, 10. And you, and you. Okay, this is for 9. Let's say, okay. You integer, it's unsigned integer. Unsigned, that it doesn't have the sign for negative or positive, so it doesn't have negative numbers. Okay, it starts from 0 and so on. Okay, and of course, because it doesn't have the sign, so the first bit from the left, it contained in the value. Okay, so integer 8 maximum or largest value will not be 127, it will be the double, 255. Okay, why this? Because it is 8 bits here. All the bits are for value, and 2 to the power 8, it's 256. Okay, and we subtract 1, becomes this, and this, still this. Okay, so the unsigned of course can store larger value from comparing to the signed one. Okay, it will be the double all the time. It will be the double. Thus we added 1 bit to the value and it doubled the value. Okay, so if I say fmt dot println math dot max integer 8 will be 255. Yes, you integer. Okay, fine. So this is about integers, and we must know that the default is this for integers. Okay, it's integer and it's machine dependable. So in your machine, it's highly possible to be 64. Okay, let's talk about floats now. Floats are decimal numbers, decimal point numbers. Okay, floats. We have two types of floats, not 10 like integer. A float 32 and a float 64. And okay, let's see this by our eyes. Okay. Let's say unsafe dot size of 1.0. 1.0 is decimal. Okay, of course it's decimal. So what's its data type? It will be 32, float 32 or 64. It is 8. 8 bytes means 64. Okay, so the default float type in Go is float 64. Of course, the difference between them, it's in bit sizes, and bit sizes this make difference in decimal point precision. Okay, at float 64, it's more accurate than float 32, but float 32 can be used for not numbers that doesn't require more precision, like for example money or any counting numbers like this. Okay, money doesn't, it just at most in most cases, not all cases, needs 3 numbers after the digit. Okay, so this. Okay, This is about the floats. There's a lot we'll see later. But if you don't need float 64, then use float 32. Explain this clearly to the language, okay. Runes, okay, let's take runes. Runes are characters, in fact, Unicode characters in Go, okay. So any symbol, any number, any letter in any language can be held or stored in runes, okay. So let's print this. If I can say rune, convert this to rune. What will it print? 65. Okay. Why? Because runes are, in other language we say characters are numbers, of course, okay. If we go to rune, what is rune? Type rune equals to integer 32. This means that rune is analyze of integer 32. Another name, just another name. It's the same. Okay, 32. And if we print, we don't need this. In fact, rune. It's by default rune. There's nothing can be put inside single quote except runes, okay. 65 it is 97 if you know this from ASCII, okay. But runes are not encoded with ASCII, they are encoded with UTF-8 encoding, and this is very good. It's a size variable, so the size varies from okay, or depending on the character. The first ones are the same as ASCII, so they just need 1 byte. Okay, if we say this and save, size of A will give us 1. Okay, 4 bits can be 4 bits. No, okay, not 4 bits. What will be 4 bytes? Of course, 4 bytes. Why 4 bytes? Because rune, it is integer 32. 32 bits are 4 bytes. There's no thing less than 8 bits here. Okay, this is size of, it's 32 bytes. Okay, from this we know that it's integer 32, and of course it clears that it is integer, it's 65. Okay, now it's 98 for small or lowercase a, small a. Okay, this is about runes, but okay, if we say, not here, in strings, we will take strings, okay, but now, and we'll take more explanation for runes, but let's explain something about data types, okay. So these are all are data types, okay. Integer 8, float 64, okay. So what data type gives us? Why we need data types? Okay, data type, say defines at least 3 things, okay. Bit sizes, okay, or memory size of data, of course. 2, values range, okay, range of values, okay. For example, integer 8 goes to 127, integer 16 goes to 32,767. Okay, so this difference, the range of values, okay, depending on the data types, also gives us the operations applied on data, okay. For example, the integer data types, we can make multiplication, subtraction, division on them. But we cannot do this for strings, of course. We cannot make multiplication for strings or texts. The same for floats. So the data type defines these things and constrain them. Okay, you have this data type, you just and only can make these operations on it. You cannot make another thing, or the compiler will complain about this. Okay, so let's see what the operations we can do on integers. In fact, there are many things. Okay, but let's at first take this one. Let's say 5 plus 6, 36. Okay, all this called expression. Okay, expression. Expression consists of operands and operators. Okay, it can consist one or more operands and one or more operators. Okay, and this expression here, 5 plus or minus or subtraction, and of course can be more, can be, okay, divide by 2. So this expression is arithmetic expression. Okay, we know this arithmetic expression. Expression. No, not this. Okay. Yes. So arithmetic. When we say arithmetic, the most important thing here, of course, these operands, but the operations themselves, because we can, okay, let's say integers can have more than one expression. Not okay, one expression, yeah, that included integers inside it. Okay, so the first with arithmetic, we have these operators and remainder. Okay, in some languages, other languages, we have this to the power 2, but in Go it does not existed. Okay, so we have this. Okay, let's say fmt.println 5 plus 6 divided by 2. Okay, what this will be the result? It's 8. Okay, 6 divided by 2, it's 3, then we add it to 5. Because the priority of division is higher than summation. If we want summation, we can use parentheses. Now it's 11 over 2, it's 5. Okay, this is 5 plus 6. It's 11. 11 divided by 2 over 2. Okay, it is 5 with something, but these are integers and these are integer. So when we divide integer and integer, the result is absolutely integer. There is no decimal point. Okay, if this is decimal, okay, the result now will be float. Okay, it's 5.5, right? Okay, for this is reminder. Okay, this is just for integers. Let's say 5 reminder 3. It will be 2, I guess. Okay. Okay, how we can know this? 5 reminder 3. It is 5 minus 5 over 3 multiply 3. Okay. This is, of course, an integer division, as we said. So 5 over 3, it's 1. 5 minus 1, okay, we don't make subtraction now. Now we have 1 multiplied by 3, it's 3. 5 minus 3, it's 2. So in this way, we can find the remainder, okay? But also we have another expression for numbers, not just integer numbers, float and integers, floats and integers. We have relational expressions. Okay. The operators are bigger than, less than, bigger than or equal, less than or equal, equal and not equal. Okay. Here we need to take another type, which is boolean. Okay. Boolean data type. Okay, it just has two values all the time, just two values. They are true or false. Okay, it can be true or false, right or wrong. Okay, yes or no. They are the same of the meaning, but here we have just true and false. Okay, let's say 5 equals 4. This is false. We know this. Okay, so the result is false. So for relational, they works on integers. Okay, not all just integers, can work on strings. We will see strings, but now we talk just integers and floats. So it works on numbers, and the result is not a number. The result is a boolean. Okay, these arithmetic operators and arithmetic expression result is number. If we make it on integers, the result is integer. If it is on floats, the result is floats. But for relational number, it can work on integer or float, but the result is boolean. Okay, as here. Okay, now if we say larger than or equal or bigger than or equal, it's true. It's bigger than. Okay. Other one are logical. Logical expression. Expression, let's say expression. Okay. The operators are and, or, and not. Okay. They works on a Boolean expressions or logical expression themselves. Okay. So this, we can say this, and 1 larger than 2. The result will be false. It's true that 5 larger than 4, but it is not true that 1 larger than 2. And says that if one of the sides is false, the result is false. Okay. We can write that the truth table of AND. Okay. Let's say it's true. Let's say true. Start with the true. False. False. No, I will not start with false. False. True. False. False. True. False. False. Okay. And here we have AND. Okay. Not here, in fact. Here. Let's say A, B. Just call the truth table. I think you know it. Okay. And this is AND. Okay, and we can write AND. Okay. True and true is true. True and false is false. False and true is false. And false and false, of course, false. Okay. If we say and, true, false and true, or true and false is true only when both of them is false, both of them are false, it will be false. Okay, this is true. For not false equals true and not true is false, of course. Okay, so it works just on one. Okay, so this operator called unary operator because it needs one operand to work on. Okay, but and or takes two, like this addition, multiplication, subtraction, and division. They are take two. But if we see the minus 5, This is minus, this is not subtraction, this is for sign. So it's also unary operator. Okay, the others are binary operators. Okay, keep this in mind, like plus or multiplication. And plus can be sign sometimes. Okay, so we have these things. Okay, the other expressions are bitwise for numbers, of course, for integer most times. Okay, bitwise expression, the operators are and, one and here, or, XOR, and invert. They are equal, but this is binary operator and this is unary operator. Okay. So there is more. There is shifting left and shifting right also. Okay. These called bitwise. So they are working on bits, not on the number itself. It's not like multiplication 5 multiplied by 6 is 30. And we don't care about the bits. When we deal with these bitwise operators, okay, so we look at the bits and we need to do that to know what the result will be. Okay. So, for example, let's take 5 and 3. What it will be? 5 and 3, what it will be? Okay, that it will be. It will be what? Okay, from my mind, 101 and 11. It will be 1, unfortunately. Okay, because I just said fortunately because it will get less number. Okay, why this? Let's go to our lovely printf to know why this. Okay, let's say binary and binary and binary. Okay, we have 5, we have 3, we have 5 and 3. Okay, so we have here 101 and 111 and 1. Okay, let's say 8 \n for line, a new line, 08 line, okay, and another 08. Okay, so this will be under each other. Okay, so we have this 101. When we AND it with this, we have what? We have this 1 and with this. Okay, this cannot take it. Okay, 1 and 1, it's 1. Like true and true, it's true. Okay, and bits 1 and 1, it's 1. 1 is for true and 0 is for false. The same. Okay. 1 and 1 is 1. 0 and 1 is 0. 1 and 0 is 1. So the result is 1. Okay. If we say 6, 6 is 1, 1, 0. Okay. The result will be 4. Okay. 1 and 0 is 0, 0 and 1 is 0, and 1 and 1 is 1. So this is 0. We know that first one is 1, first 2 is 2, and this is 4. Okay. So this is 4 number. I mean. Okay, let's say 5 plus 6 to see it at decimal or as decimal. \n value or d for decimal. Okay, so it's 4. Okay, so now we understand what does it mean. And let's take OR. Okay, it's 7. Why? Because 1 or 0 is 1. 0 or 1 is 1. 1 or 1 is 1. So this is 1, 1, 1. It's 7. It is 1 plus 2 plus 4. It's 7. Okay, 4 plus 2, it's 6 plus 1 is 7. Okay, let's go to our XOR. What does XOR says? Okay, we didn't write it here. XOR or XOR, like this, XOR. can be written like this. Okay, we will see. True and true, unfortunately false. Okay. True and false is true. False and true, it's true. False and false is false. Okay. XOR that says if both of them is equal, the same. I don't care if it is true or false, but both of them is equal, then the result is false. Okay. If they are different, I will give you true. The result is true. Okay. So this is they are both true. It's false. One true and the other is false. They are different. It's true. False and true. True, false, XOR. Not and. False, XOR true. It's true, false, XOR false, false. Let's see here. Okay. Give us 3. Why? 1 XOR 0. They are different, not the same. So it's 1. 0 XOR 1 is 1. 1 XOR 1, they are the same. It's 0. So gives us 1, 1, which is 3. Fine. This is for XOR. Okay. Let's keep it and just say not or invert. Not XOR here. Invert 5. Okay. We know 5, it's 1, 0, 1. Okay, 1, 0, 1. I didn't do this. Okay. Do you know what? Not here. Let me put it here and delete this. Okay. So the third one will be XR. Okay. This is 1, 0, 0. Okay. Okay, this is not invert. XOR, it's invert. Okay. We have this. Okay, I can delete this and delete this because we don't need it. Okay. And this. Okay. So we have this 1, 0, 1. It's 5. Okay. And we will invert it. Inversion means that each bit will be the opposite. Okay. For example, if it's 1, will be 0. If it's 0, will be 1. So this is 1, will be 0. And this is 0, will be 1. And this is 1. Why it is still 1? Okay. There's something about the sign. I'm sure about this. Okay. So in this value, because it's signed, it doesn't work like immediate or direct inversion. There is about thing about this sign and two's complement and these things in digital numbers, no, numbers, topics, you can find them. So we convert it to U integer. So there is no sign. Okay. They are unsigned. Okay. Cannot convert expression type integer to U integer. Why? Okay. Of this, no. Okay, value. But yeah, it will not make difference. Okay. Yeah. We convert it to U unsigned. So the 0, the first left 1, 0, it's not for sign. So it's okay now. Okay. So this is okay. It's 8 bits and we invert them. So 1, 0, 0 becomes 1, 1 becomes 0, all zeros becomes 1, and the value is 250. Okay. The other bitwise expressions we have here are shifting left and right. Okay, I like these two things. Okay, let's take 2. This is 5 and shift 5 by 2. Okay. Oh, we have this one. Okay, let's print it. 5. So this is 5. When we shift it left, we move the numbers to the left, okay, and put zeros from the right. We add zeros here. So this will go here and then here because we shift by 2. So becomes this here and we add zeros. And this 10100, it's 20. Okay, so this is shifting means. And also if we see that shift is multiplication by 2. If when we shift 1 once, it becomes 10. Okay, 5 becomes 10. Okay, let's shift by 1. Okay, 10. It's 5 multiplied by 2, 10. And when we shift it again, when we do shift by 2, it becomes 20. It's 10 multiplied by 2. It's 20. Okay. Let's 5101. Okay, let's shift it right by 2. It will be 1, of course, right? Why? Because we shift this 2. When we shift it the first, this will be deleted and 0 from left will be added. Then we delete also this 0 for the second shift. So it's still just 1. I hope this is clear. Okay. If you study or learn Go for software development as web development, I mean, web development or clouding, at most cases you will not use this, but sometimes you will need them, and they are very helpful in their area. Okay, they are very speed, works on bits, of course, and will help you a lot. So don't forget them. Okay. Now here we have these constants. What it says that maximum integer 8 number is 1 shifted by 7 minus 1. Okay. Why this is true? Let's take it. Okay. We now want this. Okay. This will be 127, right? Okay. Okay, we need one at least. Okay, the same. Okay, 127. Why this happens? Okay, 1. Let's print 1. Okay, 1 is 7 zeros from left and 1. Okay, so this one, when what? When we shift it 7 times, the first becomes here 1, 2, 3, 4, 5, 6, 7. Okay, so this will be 100 and not 100, 1 and zeros from right. Okay, but when we minus 1 from this, it becomes 0, 1, 1, 1, 1, 1, of course, and this is 127. So it's same for ours. What did we do? But we did it with power 2. Okay, but with shifting, it's faster and easy. Okay, so we just shift 1 by 7 and subtract 1. This is for each one. Okay, the minimum is minus 1 shift by 7, and for integer 16 by 15 and minus 1 and so on. Okay, fine. Also we have package bits, works on bits for numbers. Okay, it consists of many useful language function. Let's say 5. Okay, we know 5. It says fmt data println. We need line here. Okay, len of 5. It's 3 because it is 101. It's 3 numbers. Okay, we don't care about the zeros on the left. don't make the number. The number is 3, it's 1, 0, 1. So by this function, len 8, we can know what's the length of the number itself, how bits it takes, okay, and the number how bits it takes on bit level, okay. But in bits, there is something we need to see, okay, this thing, okay. I will explain it. Pay it your attention. Okay. What it says. In fact, the previous one in constant went constant, I don't know. Let's say okay, math dot max, not max integer. Okay, this okay. All of these are what? Are these ones, okay? Signed and unsigned, but they are machine independent. Okay, they don't depend on us, they don't depend on the machine, so their sizes are fixed. Okay, so we write them 32, it's 31 here. Okay, but this u integer, we said that u integer, like integer, is machine dependable. If it's 32 bits, will be 32 bits. If it's 64, will be 64. So how can we know the size of it at running time? Okay, by this line makes this. Okay, so let's understand this line. What does it say? It says u integer. Of course we will take this before because it's inside parentheses, it has a larger priority. So this u integer zeros. Okay, why we do u integer zeros? Let's print, not take a break. fmt print len. Okay, what? U integer zeros. Okay, it will give us 0. Okay, we don't need this anymore, but I will print it with b verb. Okay, okay, if I print just 0, it will be 0. But also if I will not say this. Let me say here 0. Okay, or let's do this first. U integer 8. It will be 0 also, the difference. Okay. Why it prints this p? Because this is not printf. Okay, now let's say my machine is 32 bits. Okay, and I will print zeros. Okay, so this is 0 in 32 bits. It's all zeros. Okay, fine. This is zeros. Okay, when we invert them, how can we invert them? By this operator. All of them becomes ones. It must become ones. Why it doesn't? Okay, let's see. It's zeros. Okay. Because I just I take this like zeros and then convert it, and it's from 8 bits, just 8 bits, not 32. Okay. So I want all of them. So okay, let's say that this is not u integer. Okay, of course we need 32. I don't know why I used u8, because u integer can be 32 or for 64. Okay, so now it's okay. This is the u integer 32 0. We inverted it, so all of them becomes ones. Okay, of course it's a huge number. Now after this, what it says, shift them right by 32. Okay, guess the result. Zeros, of course. When we shift all of them, even this one will go out and zeros becomes instead of these ones. Okay, and when we add this with one, we know that, okay, one here means what? Means all ones. Okay, not all ones, means 0 0 zeros, and the last one just one. Last one. Okay, let me take this and put this here and do this to show you. It's not one. Okay, 0 0 1. Okay, this one. Okay, all zeros 1. So when we add this with this, the result will be 0, of course. 0 and 1, 0 and 0 and 0 is 0. Okay, then it says this thing is, okay, shift 32 by this thing is, okay, and we know that the result of this is 0. So when we shift 32 by 0, it is still 32. Okay, this is not less than, it says false because it's less than boolean. No, so the result is 32. Okay, this means 32. If we print it here as a value or decimal, as you like, it will be 32. Fine. Okay, so if the u integer works on machine that it's 32 bits, the result will be 32. Okay, I wrote it here 32 to show you, just to explain, but it will be u integer. Okay, but u integer on my machine is 64. I can write 64 or don't need to do because it's by default 64. So let's see what's the difference in 64. Okay, in 64, of course, instead of 32 bits, we have 64 bits. Okay, why this is not 64? Of course, because I didn't write 64. Okay, but we will cover this. Okay, 64. Now 64, this is 64 by default. 64, 64, 64, 64, nothing. Okay, so this is 64, 0, and 64 bits is this one. Okay, we invert it to 1, so all of them becomes 1. Then we shift right these ones to left by 32. They are 64, 64's 1. So by 32 becomes this one. Okay, it's clear, right? This one. Okay, the right 32 bits are ones, the left are zeros. Okay, so when we add this with this, will give us this, of course, 1. All of them are zeros, 1 and zeros, zeros, but 1 and 1 is 1 here. Okay, so we have 1, and then what? We shift left 32 by 1. When we shift the 32 by 1, okay, we said that shifting is multiplication by 2. So we shift 32 by 1, it's multiply 32 by 2, which is 64. So this is the result, and this is the size for your integer on my machine is 64. If this is something complicated, watch it again, or find or search about it in Google to understand it better. Okay.